This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 87. Happy meteorological spring. The presentation today is titled Evolution of Increased Temporal Resolution of GOES Data and Its Effects on Select Severe Thunderstorm Applications. Our presenter, Dan Bykos from CIRA. Our discussion following Dan's presentation will be facilitated by Chris Gittro, meteorologist in charge of the Weather Service Forecast Office in Duluth, Minnesota. Just a few reminders before we get started that, as you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation. We're particularly interested in questions and comments from the field, and if you'd like to go off mute at that time and engage in discussion, we would certainly welcome that. If you are asking a question, we do ask that you sign in with your full name or specify your full name when asking a question in the chat. In the event you're using an office account, that'll help us follow up in the case we need to do so. We're also looking for future presenters, and the training team can help create training materials that may be unavailable. Brian Mata, the Office of Chief Learning Officer, can help with that. As you know, hopefully, earlier this week, we had a successful launch of GOES-T, which is hopefully on its way to becoming GOES 18. You can see there was two satellites, GOES 16 and 17, that were monitoring the GOES-T launch. And if you happen to have our new rocket plume RGB installed, this is the day plume on the left and the night plume on the right. You were able to track the launch of the GOES-T satellite with GOES. So that was very special. And for all of our forecasters, particularly in the Western United States, Alaska, and Pacific region, hopefully we will have GOES 18 data coming to you on August 1st. So it's going to be a busy period here to calibrate the new satellite, get it moved over to the GOES West position, and prepare it for operations to be fully operational in January of 2023. All right, well, thanks so much for showing that, and thanks for allowing me this brief aside. I'd like to also thank our TowerS team, Kashad Bowman, the Office of Chief Learning Officer, and the GOES Orange APSS program, as well as our facilitator for today. And of course, thanks to all of you for being with us. Without further ado, Dan has been involved with operational satellite training since joining the Cooperative Institute for Research in the Atmosphere at Colorado State University in 1998. He has developed numerous training sessions for the Virtual Institute for Satellite Integration Training, or VISIT, and Satellite Hydrology and Meteorology, or SHyMet, training courses. Dan received his bachelor's from the State University of New York, Brockport, and master's from the University of Oklahoma, both in meteorology. Dan, we are glad to have you back at the Satellite Book Club.
Thanks so much, Jordan. I'm going to look at today the evolution of the increased temporal resolution of GOES data and its effects on select severe storm applications. And why I need to say select is if we consider severe thunderstorm applications with satellite imagery and products, we can come up with a lot. These are some that I brainstormed. I could talk about the mesoscale environment, storm scale signatures, and some examples, inflow feeder clouds, cloud top signatures, derived products, machine learning like prob severe, of course, GLM lightning detection. But what I'm going to focus in for lack of time is just these first two, mesoscale environment and storm scale signatures. So what I'll do here is focus in on GOES usage for identifying storm scale signatures and analyzing the mesoscale environment to track the evolution of the increased temporal resolution from GOES, because the need for looking at these features is very obvious in terms of the higher temporal resolution. So the way I'll do that is summarize example imagery from past activities that show how we've arrived at the current GOES mesoscale domain sectors that are used operationally. We'll start in the 1990s, the GOES I through M series science test, super rapid scan operations, or SRSO. What that evolved into from an experimental and research side is the operational GOES rapid scan operations. And then after that, in the 2010s, the SRSO for GOES-R proving ground in the 2010s, and when we were looking forward to GOES-R and what we'd be able to achieve in the GOES-R era as we get closer to the GOES Mesoscale Domain Sectors that we have now. So first, just to briefly talk about some of the features that I'll talk about. Considering a conceptual diagram of various features you might see from a severe storm, you have your overshooting top. Above them, cirrus plumes. I'm not going to talk about cloud top signatures so much as I am what we're looking at down here. Flanking line and the dividing line between the flanking line, you have the inflow region of the storm. You may see inflow feeder clouds that develop within converging inflow near the strongest updraft. Example is shown down here. And then on the back side of the storm, in the outflow region of the storm, you may see lines of towering cumulus that form above an invigorated RFD. These are commonly referred to as flanking towers, and they look like this. So from a historical perspective, first of all, there was a nice webinar by Bob Rabin back on 27 January that it was very nice foundation for this in terms of a historical perspective. And certainly out of that perspective, the need for high temporal resolution data being available in a timely manner for severe thunderstorm applications was obvious. And I'll pick that up when this GOES I through M series science test started taking place in the mid 1990s. And what those allowed us to do was look at imagery at very high temporal resolution for the first time, 30-second or 1-minute imagery from super rapid scan operations, or SRSO, in an experimental format, mainly a research format to start off with. In other words, it's not available in a timely manner and not continuous for extended periods. So the idea was, can we look at these features from severe thunderstorm days and look at how critical it is to have increased temporal resolution data. Here's an example from the GOES 8 science test. This is from 31 May 1996. And the first thing I want to note is this is eastern Colorado. This is western Kansas, not an active severe weather day. Notice that the imagery is irregularly spaced in time. However, there's periods here where you have many images over a short period of time, and that's really the idea that I want to focus in on here. I'm going to stop the loop and focus in on various time periods when we had higher temporal resolution data. So I'll start off with this storm in eastern Colorado, and I'll focus your attention right here. We see the development of these low-level stratus clouds develop. The previous image time was 2242, and then we go to 2245. So this is just in a 3-minute stretch. And what happened is we see this 12-mile line arc of clouds, low-level clouds develop, and at the same time, we had a METAR that measured 70-mile-per-hour wind gusts. So we're looking at outflow, severe outflow winds from a severe thunderstorm. An obvious operational application, and obviously something you would not see readily in 15-minute data. So an obvious application here. But let's look a little bit later in time. Notice that we have a flanking line a little bit to our west and another overshooting top here. So we have another storm to our west. And what happens is the outflow that we just observed interacts with that storm to the west. I'll stop it right here. This is at 2305. Here's the outflow that I had highlighted earlier. And here's the storm of interest, kind of the flanking line associated with it. And watch how this moves westward. So I am going to advance along. Notice the temporal resolution, very high temporal resolution data, 30 seconds at times. And what happens is that outflow intersects with this storm right here. As it does, storm chasers reported a 1/4 mile wide tornado. An obvious operational application of what we see from satellite, something that you would need higher temporal resolution data to be able to observe that. So these are very important observations that were being taken place, very important research outcomes that were coming out of this, and this would lead into additional science tests. So let's go on to just some examples that I'll show. This is from 24 July of 2000 during the GOES 11 science test. We're going to look at this storm over South Dakota. And here's Nebraska down here. What I'm going to do is just zoom in and crank up the loop speed. Notice this is 1 minute data. There's a few breaks in here of more than a few minutes, but for the most part, it's nearly continuous 1 minute data. But I want to focus your attention on this region right here. We see these clouds develop on the west side of the storm. These are flanking towers. In other words, these are lines of towering cumulus that form above an invigorated RFD and are an indication of that a storm is at a mature stage or a rapidly intensifying stage. It was around this time that a tornado was reported with this particular storm, and there was also very large hail being reported with this storm. So once again, an obvious example where the higher temporal resolution data was very much needed for these transitory features, because this is a very short time period we're looking at. They kind of come and go within that 1 minute loop that we're looking at, and just something you would not see looking at 15-minute routine scanning schedule, which was normal back then. What's the operational response to this? Can we get a higher temporal resolution data available operationally? Starting in the late 90s, the operational solution to this was the GOES Rapid Scan Operations, or RSO. So we increased from 4 scans per hour to 8 scans per hour over RSO sectors that can be called over the lower 48. One disadvantage at the time is that the schedule was irregular, and if a full disk scan was taking place, you would have a half-hour gap in there. So there would be some long gaps potentially while you're trying to use this. Like I said, these can be called, so this can be used from an operational perspective, can be called by the WFOs or national centers. Very soon after this was set up, if there was a SBC day 1 moderate risk or greater, there would be an auto trigger over that area for an RSO sector. Another important component of this is improved latency and AWIPS. So if an RSO sector was called, the data would be available in a more timely manner. It would be about 7 to 8 minutes between image time and when you'd be able to see it on your AWIPS. Obviously an improvement over the routine schedule, but still room for opportunity to improve that still. So keeping that in mind, one of the advantages to this as well is you would have a closer time match to radar and lightning data. Although this started with severe thunderstorm studies, like I talked about earlier, the use cases would expand to other applications such as winter weather, tropical cyclones, fires, fog, and so forth. I'm not going to talk about those so much, but that was another important aspect that came out of this and would operationally get used for RSO. So one of the things that me and John Weaver would show in these visit training sessions is a comparison. We would show forecasters a loop of imagery at 15 minutes. This is over South Dakota. This is during the GOES 11 science test. And we would show 15-minute data, RSO data, and then kind of the answer over here, the 1 minute data. But that was just to show how this actually evolved, not so much an operational application because we weren't quite ready yet for the 1 minute data operationally. So we would ask the forecasters, when do you first discern towering cumulus in South Dakota from the 15-minute imagery? And then from the RSO imagery, same thing. And then also, when do you first see the cumulonimbus? In other words, convective initiation from the 15-minute imagery and the RSO imagery. And you get consensus answers that look something like this. So not only do we have the obvious time of detection being earlier from the RSO imagery, but just as importantly, when you would see it in your AWIPS. And that's the difference. So for the first time, we can quantitatively state what the advantage is of using RSO compared to using 15-minute imagery. And that was on the order of about a little more than 20 minutes to see a particular feature and when you would be able to see it actually on your AWIPS, because you'd be able to see it faster. And of course, you have the contextual side of this as well. You're able to see this more clearly with more images per hour, so it just makes sense a little bit more clearly when you have more images available to you as well. So just to demonstrate that, I'm going to call up the 24 June 2003 event. RSO was in effect, and just kind of shows the benefits of RSO and still some of the limitations of RSO that existed during that time. So this was a pretty high-end severe weather day that was expected in eastern South Dakota. We had a warm front that had been reinforced by an MCS during the overnight hours that's moving slowly northward. We can clearly see unstable cloud streets to the south. To the north of that, you see billow clouds or stable wave clouds north of that. What I'm going to do next is go a little bit later in time, and I'm going to zoom in right here to southeast South Dakota. So here's southeast South Dakota. I'll draw in our warm front approximately right here. And I'm going to go slowly forward in time just to demonstrate that indeed that warm front was moving northward. And I'll go ahead and draw it right here. Now what's happening at this time? A storm has developed. And how come we see this break in here? Well, we were getting higher temporal resolution data, but then what happened is we run into 21Z and we have a full disk scan at 21Z. So we have to wait from 2045 to 2115 before we get our next image. So we have a half-hour gap, and in that half-hour gap, a convective initiation took place right here along that northward moving warm front. Okay, so let's continue on. We get back to our RSO schedule here, and we see a lot of images that show the development of this storm moving northward with that warm front. And if we continue along, I'll slowly advance it, and we'll get to right here. And notice by this particular time, the overshooting top is kind of falling apart. We have a very different look to the back edge of the anvil. It's now much less crisp than it was. You can see through it in portions here. So what happened is this particular storm was falling apart. However, what it was doing is laying down an outflow, and that outflow boundary surged out to the west, and it intersected the northward moving warm front. So we have intersecting boundaries right now to watch right here. You can see that in the RSO imagery. If you're in the 15-minute mode, would have been a lot more difficult to pick up on. So again, another operationally relevant application. What happens a little bit after this? Well, here's our new storm. New storm develops west of the original storm along the intersecting boundaries. And that new storm now has the advantage of intersecting boundaries in a very favorable near storm environment, continues to grow. By this time, you have an overshooting top with that storm. I'll go ahead and move this along 2330, and it just continues to grow, continues to get more severe storm signatures. Here's a very distinct overshooting top at 2345, but then what happens next? 0Z, we're going to have another full disk scan. So our next image doesn't come along until right here, half hour later. So by showing this, I illustrate advantages of RSO. You can see higher temporal resolution data, but we still had some work to do because you still have examples like this where you get these half-hour gaps that can be just very annoying to work with if you're trying to follow along a storm's evolution. This storm would go on to produce the F4 tornado at Manchester, South Dakota. What came afterwards? GOES 14 SRSO for GOES-R. Starting in 2012, GOES 14 SRSO 1-minute data became available for various GOES-R proving ground experiments at national centers, particularly SBC, the Hazardous Weather Testbed, and also NHC and OPC as well. But one of the important aspects of this was nearly continuous 1-minute data for extended periods of time. So we wouldn't have these breaks or irregular times. So this really helped out in terms of interpretation. And then we took it to another level beyond just having researchers look at this. This was evaluated in test beds, for example, in near real-time or real-time, and feedback provided relatively quickly. This started to become more available on web pages, so you could see the data even more quickly than just waiting for the usual 8-minute lag on RSO. So strides were taking place to get that imagery back more quickly, and also it allowed for major events. Hurricane Sandy, for example, was one spectacular example to see a variety of phenomena being observed with the 1-minute imagery. Here's an example. This is from 26 April 2016, GOES 14 imagery. And the first thing to note here is just how nice it is to have a long loop of 1-minute imagery without the breaks. So now you can really get a clearer idea of the mesoscale environment. Here's a MCS outflow boundary. Here's a dry line to the west of it, and you can see the various boundaries. Here's some elevated convection from early on that left a meso high over northeast Oklahoma. So you can see a lot of different uses here in terms of improvement of the mesoscale environment, and you can see storm scale signatures such as what we see here in northwest Oklahoma with some of these storms. Now, getting back to the comparison like we were making earlier, we take this event from 8 May of 2014 over Minnesota, where we have convective initiation taking place up here, ask that same question. What is the difference between not only 15-minute and RSO, but 1 minute? So we're preparing for the GOES-R era at this point, knowing that we would have 1-minute data operationally, and also be available in your AWIPS much more quickly, about minute to a minute and a half. So again, it's a quantitative demonstration of looking at a particular feature. When would you first see this in the old days, so to speak, from the 15-minute perspective, from the RSO perspective, and then the 1-minute perspective. And it's this advantage right here of being able to see it this much more quickly on your AWIPS that would allow us to take that giant leapfrog to go from be able to use this in a way that can now be viewed as using it in a nowcasting to even a warning decision making time period, because now you're able to see it on par with the time that you're getting it on radar, lightning data, and you can use all those together. You can now use this in a true data fusion methodology, using all the data sets together, getting it in a timely manner so that you can fully make use of this in an operational way. So this has led us to our present mesoscale domain sectors. where we have 2 MDS sectors per GOES satellite, 30-second or 1-minute data over 1,000 by 1,000 kilometer sectors, where users request a MDS via the Mesoscale Mission Manager MMM tool, and these requests are prioritized by their severity or urgency. There's related SBC webinars on this that do a great job in terms of going into more detail on that. So I'm only going to summarize it here by pointing out these other webinars and just pointing out an example of this. This is from 26 May 2019. We're looking over Southeast Colorado in the Pueblo CWA, and we're looking at 1-minute imagery. This was a moderate risk day, so MDS was over this particular sector. And for this particular storm, you can nicely see many satellite severe storm signatures, the flanking line with obvious new updrafts going along it and rotating as they're going up. So it shows up very nicely. We have inflow feeder clouds on the inflow side of it that develop and go here. So transitory, and on the western flank of it, you can see flanking towers over here as well. Let me just move that out of the way, erase that. And a very important aspect of this particular day is just about as tornadoes, the first tornadoes of the day were about to occur with these storms, the closest radar from Pueblo went down. So forecasters utilize the satellite imagery in a data fusion sense. So they're looking at this imagery along with the mesoscale environment, along with trends they had been seeing on radar. So from very much a data fusion perspective to continue to issue warnings to maintain that situational awareness. So it can be used in a truly operational sense here in a data fusion way and continue to issue warnings in a timely manner, even in the absence of radar. Another example that I thought was pretty spectacular in terms of 1-minute use. This is a nighttime example. I had been showing visible imagery during the day. This is an example from the middle of the night, and we had a tornadic supercell just northeast of Abilene, Texas, moving northeastward. And in the nighttime microphysics band, or RGB, you can see right here. I'll go ahead and circle it. Those are inflow feeder clouds. And the way you would know that is their location on the southeast flank of the storm, their orientation, particularly in the early portion of the loop. You can see they're actually oriented like so, parallel to the low-level flow. That's how they would be oriented. So again, a situation maybe if they didn't have radar, or you're far from the radar and you're just looking for additional information for the warning decision-making process. Using a data fusion approach, it's possible now when you have the 1-minute data. I would argue that it would have been very difficult to figure out what was going on here. Just look at the time step. These are happening over a relatively short period of time. The 1-minute data was crucial in observations of these inflow feeder clouds. So in summary, we examined imagery for past GOES activities, which demonstrated the need for higher temporal resolution data. And I focused in on storm scale signatures and the mesoscale environment just because just the need for higher temporal resolution data is so great by studying those particular features, and provide kind of a historical perspective on how we arrived at GOES Mesoscale Domain Sectors. That's all I have.
All right, thanks, Dan. Fantastic presentation. Very neat application of the nighttime microphysics band for severe convection. Haven't seen that before like that. It might be the first time I've seen that, so very nice. But anyways, we encourage everybody to stay on for the discussion. We encourage participation from all field offices and Weather Service regional headquarters, and we ask that all the attendees specify your full name in the chat when asking questions so that we can give you proper credit. We're also going to be posting a survey link in the chat room as well, and Lee will be taking care of that here momentarily. Also want to make an advertisement for next week's presentation in a week from today on Thursday, March 10th at 12 p.m. Eastern Time. Scott Lindstrom from SIMS and I will be discussing the SIMS weighting functions webpage that was just recently released. So we'll be taking a look at that next week at this time. We also encourage everybody who might have any questions to contact the Tower S team of Lee Byerly and Kashad Bowman for questions about the SBC or for information on configuring AWIPs for satellite products. And we're going to go ahead and Dan, if you're ready, we'll go ahead and begin the discussion now. Just want to remind everybody to submit questions and indicate if you want to have the questions asked verbally in the chat room. We'll go ahead and ask them for you. So Dan, probably one of the first questions I have for you, we went ahead and you showed pretty much the evolution of rapid scan and everything like that. What do you see as next in terms of rapid scan capabilities from GOES satellites?
That's a great question. There have been some experiments done with, I believe, GOES 17 6.7 second temporal resolution data, looking at that with some thunderstorms. That was an experimental project, but I think beyond that, I think having the capability to have 1 minute data over a larger sector, ideally, over the lower 48 all the time would be great. I know there's limitations in terms of hardware and of course communications bandwidth. So that would be not only from the NESDA side, the satellite side, but also NWS side in terms of transmitting the data. Hopefully we get there someday, but I see Dan Lindsay has joined us. Perhaps he can make a few comments about that experimental data and where we're going in terms of GeoXO, if Dan is there.
Yeah, can you guys hear me?
Yeah.
Yeah, thanks for that great presentation, Dan. So yeah, back in, we were doing the science test of, or the checkout rather, of GOES 17. This would have been August of 2018. We did run some, if you scan really only a mesoscale sector and you don't do CONUS and you don't do full disk and scan as fast as possible, turns out you can scan every 6.7 seconds, which we know ahead of time is overkill, but we did it for the purpose of seeing sort of what is it, does this give you any extra information? And it doesn't do any good to show 6.7 second loop over WebEx or whatever this GoToMeeting, I guess, because the limitations of the bandwidth will not allow you to see everything. So I'm putting a link in the chat to one of these loops. It works best on a desktop or a pretty good laptop if you have it, to show you what it looks like. And this is, we did capture some supercell rotation. This is Western Kansas back on 18 August of 2018. And there's two storms that you can clearly see storm scale sort of side of the cloud rotation in this loop. One is in the very center of the image, and the second one is at the sort of northwestern edge of the image, especially later on in the loop. So you can play with that if you want to. But basically, what we concluded was if you want to increase the, I guess there's no reason to increase the temporal sampling above 30 seconds unless you improve the spatial resolution of the viz even further. Remember that this is 500 meter subpoint resolution. If we go to 250 meter in the future, which is what we're going to shoot for GeoXO, then it might make sense to go with time steps 30, less than 30 seconds, say 15 seconds, 20, something like that. 6.7 seconds is definitely overkill, but it does allow us to see some pretty cool things like this storm scale rotation.
Excellent, Dan. Thank you for that. Just a follow-up comment from Steve Goodman. Dan, during the GOES 16 post-launch test, I recall with NASA ER2 observations of cloud top turrets by the scanning HIS, the SHIS cloud top temperature was 10 to 15 degrees colder than what was observed by the ABI. And then let's see, what else do we have? Tim Schmidt also adds, thanks for the memories. More on GOES 14 SRSOR from 2012 to 2016, and Tim provided a link as well. Also, many post-launch GOES science tests for GOES 11 to 15 had NOAA tech reports. Also, he thanks Scott Beckmeyer for the Sandy images, since this was after the planned time of the SRSOR, and he suggested we ask for more time. Also from Scott Lindstrom made a comment, GOES-R data would not have been the impact that it has if it were not still, having a hard time reading that there, about 20 minutes to get the latest satellite imagery and AWIPS, as was normal not too long ago. Yeah, absolutely. So kudos to everyone involved in that, making that a very important improvement. So I think that's probably one of the things, Dan, that I, definitely had a takeaway from your presentation. What used to be 25 minutes, 8 minutes, and now pretty much we're getting data within the minute. Uploading to AWIPS has just revolutionized the technological availability of satellite data for the forecaster. Steve Stavish also says, thanks, Dan. That was a great historical timeline for review and perspective. Could you refresh us on the current SRSO display archived in AWIPS with overlapping mesodomains? Initially, this capability had a challenge in AWIPS with product time labeling, if I recall correctly. If there were overlapping mesos, is there anything special forecasters need to do in order to see the 30-minute temporal resolution? I'm sorry, 30-second temporal resolution.
Yeah, I do remember that being an issue at some point. I don't think it is anymore. If somebody knows the answer to that, can they speak up, please?
This is Bill Line.
Hey, Bill.
There is something special you need to do, and I've shared it with the Tower S group, but maybe I'll ping them again. It's an extra menu item you could have that I did on my local AWIPS. You can do it, but there's just a little configuration file modification you need to do.
I guess for my curiosity, how often, since we've had GOES 16 and GOES 17, have we employed the 30-second update or temporal resolution utilizing two mesosectors?
I should say that if 30-second imagery is requested, it works in AWIPS. If it's not requested, but you have two 1-minute sectors that are partially overlapping, that's when you have to do this modification I was talking about. But
gotcha.
If it's requested, it'll work.
Thank you,
Chris.
Bill. And I just was going to note here that thank you, Bill, for putting together this nice loop that I showed here from Southeast Colorado as well.
This is Dan Lindsay again. To answer, I think it was Chris's question about the frequency that we get with 30-second imagery calls. I think it's pretty rare. The data exists to look that up, but I know it's been done a number of times, and it's mainly been done on the research side. Like we did it a lot during the science test. I think maybe there was some of the Relámpago campaign in Argentina, but I think for the most part, forecasters are happy with 1 minute. That's my perception, that it's rare that you can get something dramatically different from 30 seconds that you're not getting with 1 minute.
All right, thank you so much. That's great. I'm not seeing anything else. Am I missing anything, guys?
One more question from Steve there, I see.
Oh, sorry, Steve. For Bill, from your SPC experience, how did ABI best add to what you already knew from radar?
I think it was SPC. A huge part of their job is, before there's any radar echo, I'd argue maybe the most important part of their job. So it was in that pre-convective environment, monitoring the evolution of the Q field character of cumulus clouds as you approach convective initiation before any radar echo is where it really helped them the most. SPC, those forecasters are really experts in analyzing satellite imagery, and to have this higher temporal resolution imagery available to them to be able to see when the Q field and the cap is just starting to break, that's where it really provided the most benefit.
Absolutely. All right, I don't think I've seen any additional questions at this time. So Jordan, I think I'll go ahead and pass it over to you.
Okay, thank you so much, Chris, for moderating, and Dan. I really appreciate that presentation. As has been mentioned already, next week the Satellite Book Club continues. We got Scott Lindstrom from SIMS, and Chris is back to talk about the SIMS weighting function webpage. So we dig a little bit deeper into how we interpret water vapor imagery. Feel free. I hope you're planning on joining us next week to learn a little bit more about this great capability. And I think it can be very useful, particularly for those interested in getting a little more, extracting a little more value out of their satellite imagery. So please tune in next week. I will just make a brief note about this presentation and the 30-second imagery. The Weather Service Office Observations is actually exploring a 2.5-minute CONUS mode. So you might see a little bit in there. You know, Tim Schmidt's noting the Weather Service requirement, and to some extent we're limited by how quickly the ABI can scan from left to right and everything we need to scan within a 10-minute period. But we are looking into a 2.5-minute CONUS period, CONUS update, and we'll keep you informed about that. So if you've heard about that, the rumors are true, something that we are exploring. Okay, just to wrap it up here, if you need assistance with the configuration of satellite products, our TowerS team is standing by. John Evans and Lee Byerly. I almost sound like I'm calling in for donations or something, but John Evans and Lee Byerly are ready to help you with anything you need related to satellite imagery in your AWIPS. And of course, if you need information about the Satellite Book Club, Kashad Bowman's there. All right, folks, it's been a great week. GOES has launched. We'll keep you updated on the status and future book clubs. Please join us again next week. Stay well and happy meteorological spring. Take care, everybody.